It's a great pleasure to introduce Professor Máté Wierdl, who is going to talk about random differences in Zimmer's theorem. Please.
Thank you very much. So I'd like to thank the organizers for inviting me and also for the nice ride we have every day from the hotel to this place. It puts us into a nice mood. So let's see whether I can handle this thing. So here I would just like to outline very quickly what I'm going to talk about. So first, a little history behind the problems I'm going to talk about. Then we introduce the main course of the lecture, typical or random sets. We will see some examples so that we can develop, if not necessarily a feeling for these random sets, but at least for the formulas, so that we see a little bit better, because the formulas are slightly abstract if you are not used to seeing them. Then there will be a conjecture or a problem, however you want to call that. I think now all three of us, so Francisca Nikis, Lessing, and myself, we agree on the truthfulness of these conjectures. So we had some arguments in the past, but now we agree. In this first part of the talk, we are just talking about so-called intersective sets. No ergodic theory is going to be seriously mentioned at all. And actually, it's an interesting feature of our results that the combinatorial applications, in fact, admit completely elementary proofs, so completely devoid of any ergodic theory. But the methods allow us to prove some, at least in our opinion, pretty interesting results in ergodic theory, namely almost every convergence results for double averages, so-called double averages, which are rare and usually difficult. This one is not difficult, amazingly enough, but it looks impressive anyways. There will be an ergodic theoretical conjecture after the ergodic theoretical result. And if I have time, I plan on talking for about 50 minutes. If I have time, I will give an outline of the proof, or maybe just partial outline of the proof. That should be 5, maybe 10 minutes. We'll see if we have time for that. So, okay. So let's start with the history of the thing. So let's just see, first of all, the definition, although I am assuming that most people are familiar with this. So what do we call a sequence of integers of positive density? Well, first of all, the upper density of a integer sequence is defined in this way. Let me see. So in this way. So what we see here is we consider all the elements in the sequence which are less than some prescribed m, and we divide by m. So this measures actually the proportion of the elements of the set in the interval 1 through n, or m, or 0 through m. Okay? And we say that maybe I say this here. No, I didn't say that. So a set is called of positive density if the upper density is positive. Okay? So the main result, or classical result, using János's expression, although this is really classical, unlike the Green Tower result. Classical result of Semeredi from 1975 is that if we take a set of positive density, then for any L, it contains a L plus 1 long arithmetic progression. So this is what we see here. What am I doing? Oh, here we go. So here we see, I pressed the wrong button. So here we see all these elements, these L plus 1 elements are contained in A. So L plus 1 long arithmetic regression. One way to generalize this result, there are several ways. One way is that instead of considering subsets of the positive integers, one considers positive density subsets of the primes. This is the content of the Green-Tau result and generalizations, which we heard this morning from János. And the other possibility, well, there could be some other possibilities, clearly, but one main line of research is when, because in the original theorem of Semeré, this difference R of the arithmetic regression is not prescribed. It just says it's some kind of positive number. And so we prescribe a set from which we could possibly take this difference R. So what can be these sets? Well, first of all, let's just, so that we can talk a little bit easier about these things. So we fix a positive integer, and we say that a set is of a set of positive integers is L recurrent or L intersective if any set of positive density contains a L plus 1 or arithmetic progression where we prescribe that the difference has to be from this set R. Okay, so the set R, which we call L recurrent or L intersective. We'll explain this terminology a little bit later. Sometimes, I may not do it, but sometimes we refer to this L as the order of intersectivity. And let me remark that this is not a vacuous concept. So for any L, one can construct a L intersective set which is not L plus 1 intersective. So there are some sometimes serious, sometimes not so serious difficulties here. So let me explain the terminology. Why do we call such a set intersective? So having this L plus 1 long arithmetic regression in my sequence, A, is the same as saying that we consider this intersection, L plus 1-fold intersection, and that we demand that this is non-empty. Okay, so for some R, where the R is from the supposedly prescribed set. Okay, so, and now what happened? It didn't go? Okay. Now, why do we say, and actually equivalently, that a set is L recurrent? So there is a completely equivalent ergodic theoretical reformulation of, well, not exactly this inequality, but actually it turns out to be equivalent with that one. So there is what they call the Fürstenberg correspondence principle, which says that being L intersective is exactly the same as saying that if we take any dynamical system and we take a set of positive measure, then for some R from our prescribed capital R set, we have that the measure of this L plus 1-fold intersection is positive. So these two things are completely equivalent because of Fürstenberg correspondence. and I will use L recurrent or L intersective interchangeably. So let's see some history about L intersective sets. So let's look at the squares, or more generally the kth powers. So here. And so k is a fixed integer, and we consider the k powers. For L equal to 1, and that's the same as just demanding that the set with positive density has a difference which is a square. That was a conjecture by Lovász, and it was answered by Sarkozy. And actually later, well, no, not immediately, but almost immediately, he generalized it to kth powers as well. So this is the case for L equal to 1, where we don't really talk about arithmetic regression, I would say. And for arbitrarily L, this was proved by Bergelsen and Leibman. What is that? Not really 20 years ago, but almost, so soon 20 years ago. And actually, it's not just for squares, so for arbitrary k powers. Actually, one can talk about more general polynomials as well, but let's just concentrate on this example. So now we can consider shifted primes. Vitali Bergelsen mentioned these sets. So what we do is we take all the primes and we subtract 1, or maybe we consider another set, namely we consider the primes shifted forward by 1, so we add 1 to them. So we consider the prime minus 1s or the prime plus 1s. So this is a set to consider. No other shifts of the primes can be considered for recurrence, even for one recurrence. And for L equal to 1, this question was raised by Erdős, whether the prime minus 1s form a set of recurrence and or a set of intersectivity, and was answered by Sarkozy soon after. But this was only for L equal to 1. The L equal to 2 case, so the higher L case was really complicated. And for L equal to 2, it was solved by, I just refer to my friend Frantsikinakis, sorry. See, because I always mispronounce his name, so I just write F for his name. Host and Cry in 2007. And I know that I forgot to put the year here. Maybe it's a 2010 paper, if I remember correctly, by Woolley and Ziegler, where they prove actually the case for arbitrarily L. We can also consider, and actually for our talk, these sequences are possibly more interesting than the other sequences, namely when we consider non-integer power. So for example, we look at all the 3/2 powers of integers. Of course, then we have to take integer parts. So we take integer parts of n to the 3/2, or more generally take a non-integer positive delta and consider n to the delta integer part. So then it seems that I was the first who wrote this down, that for L equal to 1, these sets form these are one intersective. But Boschanitz definitely, if one reads his corresponding paper, I think 6 years earlier, it's completely clear that he had the result in mind. He just didn't write it down for some unknown reason, to me at least unknown. So, but for the L greater than 1 case was settled by Frantsikinakis and myself in 2009. The reason why these sequences are perhaps more interesting for this talk than the other sequences, because they behave more like random sequences, and our main interest is random sequences, so randomly generated sequences. Before we get to them, so just let me, there are some general results about intersective sets, which are good to know, and you can look for these kind of structures in some given, if somebody gives you a sequence and asks you whether it's a set of recurrence or not, you can try to look for these kind of structures and then maybe quickly decide whether the given sequence is intersective or not. So if you take a lacunary sequence, so lacunary sequence is defined like this. So the ratio of consecutive terms is bounded away from 1. Okay? So if that's the case, for example, if you take the powers of 2 or powers of any number, then the sequence is not intersective, and this is a result of Erdős and Sárközi. Also, if we have a set R, which contains arbitrarily long intervals, then it will be a L intersective set, and that's actually a not too difficult consequence of Semredi's theorem. If one looks at the original statement of Fürstenberg's result, for example, then actually this is included explicitly. In Semredi's result, it is not included explicitly. Because Fürstenberg formulated his result in terms of basically Banach density, although I'm not sure that he used exactly that terminology. Anyways, so arbitrarily long intervals imply being L intersective. So now what we want to look at is what happens with typical sets. So there are all these special sets. We know that they are intersective. And the question is, what if we take a typical set? Is that a set of, is that an intersective set or not? And well, what we mean by typical is that we randomly, there might be other definitions of typical, but we randomly select integers according to some prescribed probabilities, and we'd like to see whether almost surely, with probability 1, we would get a intersective set or not. So, I mean, for example, maybe I should write that down. So, what we can do is, maybe we select it, given an integer, we select it into our random set with probability 1/2. So we flip a coin and we decide whether the number will be in my set or not. Or, well, of course, in this way, we are going to get a set of density 1/2. How can we get something which has 0 density? For example, if I take this probability, so I will take the nth integer into my random sequence with probability 1/√n, and so in this way, I will get a set which increases as fast as the squares. Maybe we'll talk about this a little bit. As fast as the squares, although they have much better properties than the squares. And we can ask whether this is a set of recurrence or not. Okay, so we make this random selection notion completely precise in the following way. So first of all, we are given a sequence of probabilities. So for example, 1/2 or 1/√n. And capital U1, U2 will be an independent sequence of selectors, so 0, 1 valued random variables on this probability space. So 1 is taken, so the value 1 for un is taken with probability un, and the 0 is taken with probability 1 minus un. Okay? So, and we view un, so we think of un, the un sequence, so u1, u2, and so on, as the indicator of my random sequence. Okay, so that's the indicator. For combinatorics, this is a well-known thing. And so R omega is defined exactly this way. So whenever the un is equal to 1, then we take n into my random sequence. Now we introduce a terminology, and this is very important to keep in mind, although we keep forgetting this. So we say that a random sequence has some given property if there is a set of omega prime of full probability, so that the random set R omega has the property for all omega in omega prime. So it happens with probability 1. Okay? Maybe I remark that we are not talking about, whenever we talk about results, we are not talking about really the random variables. Usually we just prescribe the sequence of probabilities, and then we talk about properties of a random sequence, and that means take a independent sequence of random variables with the appropriate probabilities there or distribution there, and then get some description of the results. So maybe some warnings about what kind of probabilities we take. If I get to describing the outline of the proof, then we will see the significance of this assumption, namely, and this is a pretty natural assumption, that we assume that the sequence of probabilities is decreasing, not necessarily decreasing down to 1. For example, it can be a constant 1/2. And also, we assume that R omega, so this random sequence, is an infinite sequence. It's an infinite set, and we achieve that just by assuming that the probabilities sum to infinity. Okay, so these are pretty natural and usual assumptions. Probably I will forget to say this all the time, that n has to be large enough. So if I say something and the result looks suspicious, assume that n is large enough. All right. Now, so now we start developing a little feeling for this kind of thing. So first of all, the strong law of large numbers says that with probability 1, the un omega divided by their expectation, the sum of their expectation, converges to 1. So this is Kolmogorov's generalization of the usual strong law of large numbers. What is important for us to see, and I think this is what I have in the next line, yes. So what we should keep in mind, that the counting function of R omega, so namely the number of elements in R omega, which are less than or equal to capital N, is exactly this sum, right? So the sum of the first capital UNs. And the strong law of large numbers says that this counting function is perfectly well described by simply the sum of the first capital N UNs. Okay, so that's what we see here. Okay. So basically we can use these two quantities interchangeably. Okay, so some examples. So what we are going to see in this little chart, we will see the name of the sequence. Sometimes, so the name of the sequence, what the UN looks like, what the sum of the UN, so namely the counting function will look like of the random sequence, and L equal to, in the next two columns, L equal to 1 and L greater than 1, we will see a green check mark if the set, the corresponding random set is set of recurrence, and a red cross if it's not. Okay, and there could be question marks, and eventually there will be lots of question marks where we have no idea. And of course, that's the attraction of the subject. So when we take the coin flip, so this was our very first example, so we decide each integer to be taken into the sequence with probability 1/2. Counting function is, of course, capital N over 2, and this is a set of recurrence, and this is because, as we know, that these sets with probability 1 at least, they contain arbitrary log intervals. So you remember the first warning we had, that this is a good way of not thinking that this is something complicated. It's not working for some reason. So the random primes, we are just developing a little feeling for these UNs. So random primes, when we take each integer with probability 1 over log n, supposedly the primes behave like that, right? But they have some additional arithmetic properties. The counting function is n divided by log n. And again, the reason is exactly the same as before. With probability 1, the random sequence does contain arbitrary log intervals. So the generalization of this is when we divide 1 by a function of n which goes to infinity slower than any power of n. So that's what I wrote here as n to the little o1. I don't know how official it is, but, and then of course the counting function will be n to the little 1. So, is that so? 1 minus, yeah, 1 minus, yeah, okay, 1 minus, I was wondering about that. So 1 minus little 1, that's what we are talking about here. And again, for this you can prove that easily, actually, that such a random sequence contains arbitrary log intervals. Okay. So now the question is, what happens with random sequences where you don't have this structure? So namely the arbitrary long interval structure. And so what if we consider positive, we divide 1 by a positive power of n. And so the very first thing, very first result which appeared was when we divide 1 by n to the 1/3. So the counting function is not exactly capital N to the 2/3, constant times, but I will leave out the constants because the order of magnitude is important for us. And for L equal to 1, this is a Erdős-Sarkar result. So actually this is exactly how they examine the question. So what happens with typical sets? This is exactly what they asked. And they proved in 1978 that so the random set with probability, so the random set is 1 intersective. For L equal to 2, this is a recent result by F, L, and myself. Actually, the paper appeared last year. It seems that it appeared last year, but actually it appeared this year. And actually it was proved independently by Michael Christ as well at Berkeley. And I tell you that for L equal to 3, we have no idea. So I didn't write it up in a chart because then it wouldn't have fit well enough. So we have no idea. Now comes the case of the random squares, which I mentioned as a second example. So for L equal to 1, it's a result of a more general result of Bose-Chernytson, that it's the random set is intersective, but we don't know even for L equal to 2. So this is the first unsolved problem. So we can get arbitrarily, actually, as you will see, we can get arbitrarily close to this n to the 1/2, but we cannot reach it. Okay, so it's really, I don't know, I can call it annoying or embarrassing, however you want to say it. Now, so when we divide 1 by some positive powers of n, then we get sequences which increase to infinity as fast as a polynomial. So what happens with sequences, random sequences which increase faster than polynomials? So for example, let's take, what did I do again? Here we go. So let's take, say, log n divided by n. In that case, the counting function is log capital N squared. And L equal to 1, again, Bose-Chernytson. It's exactly the same paper as this one. Okay? And actually, the log n can be replaced by any function which goes to infinity, arbitrarily slowly. You want to make sure that the probability sequence of probabilities is decreasing, but otherwise, so you can just put there arbitrarily slow function for the log n. Of course, I don't even have to say that for L greater than 1, we don't know anything, even for L equal to 2. Now, if we look at, not immediately 1 over n, just 1 over n times log n, so the counting function in this case is log n, and in this case we know that we cannot have a set of recurrence. And it is because, actually, with probability 1, this sequence is lacunary. So this is actually not too difficult to see. On the other hand, if one looks at the case of 1 over n, so if we look at the 1 over n, it's pretty complicated. to decide that, in fact, this is not a set of recurrence. I call it dense lacunary because one can select basically a subsequence of the sequence of density 1, which is lacunary. So it indicates that this should be a bad sequence, but there is still a zero density subsequence which might somehow cause some kind of recurrence. And so there is a paper by Bourgain where he examined a little bit differently generated random sequences and found that that sequence was not a set of recurrence, and Anthony Quast deciphered that paper for us and figured out, and in fact it can be applied even for the 1 over n case. So what we see is, if we go back for a minute, that Boscher-Nielsen result, where we can replace this log n by arbitrarily fast increasing function, is sharp. So that's nice to know. Okay, so let's go forward. Why doesn't it go forward? Okay. So what is the theorem we have? So the best theorem we have is this. So this is by Frantsikinakis, Lessing, and myself. So for any fixed L, if we take a decreasing sequence of probabilities, I just repeat that always standing assumption, and we multiply the sequence of probabilities by n to the 1 over L plus 1, and if we find that this goes to infinity, then the random sequence is L intersective. So what you see is that this exponent here of n unfortunately goes to 0 as L goes to infinity, so L gets bigger and bigger, and we will examine for various L's so that we can get used to this formula a little bit better. And maybe we will appreciate this result more or less, depending on your taste. So it's not moving again. Okay. So I'd like to emphasize at this point that when we talk about random sequence, then actually we are talking about so sequences which are selected with probability 1. So this is just a reminder of what I said in the definition originally. All right. So this is the condition of the theorem. So let's examine various cases. So when L is equal to 1, then actually our result is not very good, right? Because it says that if un times n to the 1/2, so we don't reach the random squares case, that's excluded. Then we get a intersective random set. On the other hand, the best known is Boscher-Nielsen's result. So this is exactly Boscher-Nielsen's result, that un times n, if it goes to infinity, then we have a set of recurrence. So that's not so good. Now when we look at L equal to 2 case, right? So then the 1 over L plus 1 becomes 1/3. Okay, so this is what our result says, that if you have this assumption, un times n to the 1/3 goes to infinity, then we get a set of 2 recurrence. But the best known is not this. So for this case, the best known is when we take probabilities which generate a random sequence arbitrarily close to the random square. So un times n to the 1/2 goes to infinity. And so this result was, this was in this paper which appeared last year. And again, I just repeat that Michael Christ also achieved that result independently from us. Now, when L is equal to 3, okay, so this is the result, n to the 1/4. The best known was exactly the same. Actually, we improved it with a little log n factor, but let's just say it ties the best known result, the n to the 1/4. So the excitement comes only now. Okay? So, because in case of the L equal to 4 case, we have a record. Okay? The previously known case was, which is not coming, or it's coming now, it was n to the 1/8. Okay, so. Okay? Now, those who know the van der Korput lemma, van der Korput trick in ergodic theory or number theory, then they recognize or they can suspect why the heck we have, in previous results, we have 1/2, 1/4, 1/8, and in general we get powers of 2. And it's because as we use the van der Korput lemma 1, 2, 3, as many times, then unfortunately it gives a exponent in n which goes to 0 exponentially. So this is exactly what we see here. So in case of L greater than 4, the previous best result was this. So n to the 2 to the minus L plus 1. Okay. So that was the content, among other things, that was the content of this 2012 paper by us and Michael Christ. I just saw his paper only on archive, but not published. Okay, so this exponential thing was improved to this one, and the novelty of the paper, I think, that the proof is simple, and it is not using van der Korput lemma. So, and we knew that if we wanted to improve this result, so the n to the 2 to the minus L plus 1, that then somehow we had to prove results without using van der Korput. So, okay. Now, so what is the conjecture here? The conjecture is that exactly the same probabilities which gave us random sequences, intersective random sequences in case of L equal to 1, they should work for arbitrary L. Okay, so this is exactly what is said here. So suppose the decreasing sequence of probabilities satisfy un times n goes to infinity, then the random sequence is L intersective for any L, not just L equal to 1. So, but again, our method is such, amazingly enough, that this 1 over L plus 1 judge Oh. No, I was not prepared for this at all. Okay, okay, so here we go. That's the conjecture. So now, I think we want to talk about briefly ergodic theoretical results, because the same method, elementary method, can be used to prove some pretty good results in ergodic theory, or surprising results. So let me just state the result, and then I will tell you how it could relate to other existing results. So first of all, we have this rather complicated assumption here, that un times not n to the 1/2, but un times n to the 1/2, and the speed is a little bit slower than the n to the 1/2. There is this logarithmic factor. But you can disregard it if you want to understand the result. So just imagine that un times n to the 1/2 goes to infinity. The reason, maybe I should say that if we just have un times n to the 1/2 and not this logarithm here, then the conclusion of the theorem, which is coming up, would be convergence in L2 norm. But the exciting thing is that we can prove actually almost everywhere convergence results. If we improve the speed here, which means actually we don't improve it, we no, what's the opposite of improving it? so it's a worse speed, but anyway, so if there is an extra speed in the probabilities with which they go to 0, so if there is an extra speed here, then we can actually conclude almost every convergence. And this is actually a pretty general principle or philosophy that once you have mean convergence, then you can improve the result to almost every convergence if you put in a little speed. So you can see this all the time. Okay, so what is the result? So if we have this assumption that the un times n to the 1/2 goes to infinity, so this is just barely worse than random squares. That's what we are looking at. Then if we take the random sequence in the usual way, then in any dynamical system, for bounded functions fi, these so-called double averages. Okay, so we take Tn, the first function f1 of x, times t to the Rn, so that's that random power, f to x, then the convergence takes place to f1 times f2, so these are the invariant projections of the two functions, f1 and f2. Okay, so so I explained that. Maybe I should say that in order to have the convergence to this to the product of the invariant projections, this is why we have to have, and this is actually a not only sufficient but a necessary condition, we have to have that the un goes to 0. Okay, so the un goes to 0. That just means that the random sequence has 0 density. Okay, so and now, so what is interesting about this? It will be the so what they previously knew about almost every convergence, this was Burgen's result, a very complicated result. When you look at these kind of averages, you look at Tn f1x, T2n f2x. Okay. So here you have two linear exponents of the t, and then you have almost every convergence, and here already the convergence is not to the product of the orthogonal projections. Okay, so what we see here in the exponent is two different rates. So this is linear, and actually here we can put any linear rate. So this is linear, but this is a non-linear rate. And this is the first result we know of, that actually you have double averages with non-linear rates, and you can prove convergence. You may ask whether this n can be replaced by another random sequence. Yes, it can be. The important thing is that the two random sequences don't increase too fast. So it is described by that rate, and they should not have the same rate. Okay, so that's just a remark. Yeah. Oh, that's very different because it's not known. N and n cube are not known. Mean convergence, yes. Oh. So yeah, right now I don't know. Good question. No. Yeah, I don't know. I decided I don't know. Certainly we cannot have the convergence. Okay, what I can tell is that certainly we cannot have the convergence to the product of the orthogonal projections, because even if we don't have this factor, then we don't have convergence there. But otherwise, whether there is almost ever convergence right now, I don't know. Good question. Yeah. Sir? N cube is Burgen alone. If there is nothing there. But once you have double averages. Maybe there is something. Yeah. What? L2. Yes. L2. Yes. So it's just a usual invariant projection in the Miner-Galdic theorem, whatever was that. Yeah. Okay. The previous best result was, this paper improves our original result a year ago, where instead of having n to the 1/2, which actually is definitely the limit of the method, we had so instead of n to the 1/2, basically we had a n to the 1 divided by 14. So we knew that even at the time that the limit of the method will be this n to the 1/2, but we just could not really get that at the time. I remark that, and actually one could talk about the so-called commuting transformation case even for recurrence, but I'm not going to do that. So when we, instead of looking at just powers of the same transformation, so we look at averages, so this kind of averages when we look at two commuting transformations, f1x and t2 r and f2x. So if we look at this kind of averages, so where t1 and t2 are commuting transformations, then actually we can have the same conclusion, but not with this nice elementary method. So we can have the same assumption, but we look at these more general averages for commuting transformations, and we can conclude the same thing. So even for commuting transformations, and I remark that these results for commuting transformations are they just don't have any precedence, because Burgen does not have the result for commuting transformation. So the generalization to that one seems very complicated, at least at this point. But that's not, so that uses a combination of this method and Fourier analysis. So that's not so pretty. Okay, so how far am I? Of course, the question is what happens when un is equal to 1/2, so the random square case, and we just really don't know. Maybe, because I forgot to say this, I'd like to emphasize that our method nice and elementary, but it is powerless for commuting transformations. So just... Yeah, of course I'm... and to the, yeah. So this is n to the minus 1/2. Thank you. Exactly. I should have said that. So that's a question. What happens then? And the commuting case uses van der Korput as well. So, okay. So there is a conjecture. If we wanted to say just mean convergence, then we would have un times n go to infinity. But if we want to conclude almost ever convergence, then some kind of speed, probably some kind of logarithmic speed, is needed. Actually, probably even log n would be enough. But let's just put it this way: even this seems not really available at this point. So un times n goes to infinity, and we have to assume that the random sequence has zero density. So this is a standing and necessary assumption, so that we can identify the limit nicely. So then we should be able to conclude what we concluded for the limited random sequences before. So these double averages should converge to the product of the invariant projections almost everywhere. So that's the conjecture to work on, and this is what we call semi-random, because at least as the result is formulated, this is a semi-random average, right? So this factor has random exponents, but this is not. So, I don't know how much I should say about the proof, because it would require 10 minutes, so probably I don't really want to say much. Should I start? Maybe I just say a few words, just really a few words. I have, I think, 3 or 4 slides on this one. So what is the idea of the proof? So, and remember, we don't want to use the van der Korput trick. The whole thing, the main reason why we are looking at these random sequences, so that we see some way of improving results without using van der Korput, because van der Korput just really limits us with the random sequences. So what we try to prove is the following. We try to show that if a set has a positive upper density, then this limit infimum is positive. So actually what we would like to show just simply that for some n in our random sequence, this inside here is non-zero, right? So that's all we would need to show. But what we see here is that with this un, we select only those n's which belong to the random sequence, and then we take the averages. So actually what we show is that on average, we will have this upper density greater than 0. Okay, so this is a pretty usual thing to do, at least when you do ergodic theoretical proofs or ideas using ergodic theory. So now what? Now the first little technicality here, that instead of, because notice that here we divide by the counting function, the actual counting function of my random sequence, right? Because that's the number of elements here in the sum. Because of the strong law of large numbers, actually we can divide by just the expectation, right? So that's just really a minor, absolutely minor technicality, and so this is our task. Now the second one. Now let's look at the expectation, well, maybe in quotes, of these averages. The expectation, it just means that we take the expectation of the un, which is little un here. So we look at these averages. Well, when we look at these averages, then actually the limit is going to be greater than 0. And this is exactly the point and the only point where we are using that the un sequence is decreasing. Because since the un sequence is decreasing, so a simple summation by parts argument shows that if I replace the uns by 1, so here I just cancel the uns, and here I divide by capital N, then we know by Fürstenberg's result that this limit is greater than 0. Okay, so this is just a weighted version of Fürstenberg's result. Okay, so we know the good thing about the expectation, and the natural thing is to compare the random average with the expectation. So what do? We show the following, that with probability 1, we have that the difference, so we take the absolute value of the difference of the two averages, right? So we take the difference of this average and this average, which is right here, and we take the sup in every A, and the reason for that is, don't forget that we want to say that our random sequence is a set of recurrence for every set, for every single set, of positive density. So therefore, a good way of assuring that is that somehow this sup in A appears. And what we show is that with probability 1, that this thing goes to 0. So I think I just make one more. So just a couple of more jumps or steps in the proof. So remember that the assumption in this case, so in the L equal to 2 case, is that the sum of the un divided by n to the 1/3 goes to infinity. Right? So that's the assumption. And of course, then we can find a sequence of epsilons. Actually, they are not necessarily strictly decreasing, but it doesn't matter, actually. So they go to 0 pretty slowly. How slow? So they go to 0 slowly, but in such a way that this ratio is still big. Okay, well, you can imagine that this ratio still goes to infinity. If you want, maybe that's the best way to imagine that. Okay, so this is how we define an epsilon, sequence of epsilons. And now the main inequality is this. So the main inequality is the following, that we took, well, the supremum on every A. So we want to make sure that again, the random sequence will work for every A, so not just for a fixed A. And so what is the probability that the supremum of the previous slide, because this supremum is supposed to go to 0, so what is the probability that this supremum is greater than epsilon n, where epsilon n goes to 0, as you saw it before. And what we prove is this exponential estimate. And if you look at this part here, this part is basically n to the 1/3. So this goes to 0 very fast, although because of the Borel-Cantor dilemma, all we would need is that it's summable. Okay? So this goes to very fast, summable, and so by Borel-Cantor dilemma, we can conclude that this supremum here goes to 0 almost surely. Okay, so that's the main idea. I just make one more remark. If we consider the case when we don't take the supremum in A, so if we don't take the supremum in A, just for fixed A, then this estimate, with a different C from here, but of course we could put there the same C. So this is an immediate corollary of Bernstein's inequality. Bernstein's inequality in Russian, I suppose. Okay, so the difficulty is really to handle the supremum there, and we handle that in just counting some indicator functions. So thank you very much.